I want you to picture a scenario. It's a Tuesday morning. You are a clinician, maybe an infectious disease specialist.
Okay.
You have a patient, a 35-year-old man. He is relatively healthy, but he's dealing with a new HIV diagnosis. It's heavy news, obviously, but in modern medicine, this is manageable. You have the toolkit.
Right. It's absolutely not the death sentence it was in the 1980s.
Right.
We have highly effective antiretrovirals.
Exactly. So you reach for the standard of care. You prescribe a regimen containing a drug called atazanavir. You do your due diligence. You check his labs, liver function.
Pristine, I'm guessing?
Pristine kidneys, working like a Swiss watch. You send him home. You feel good about it.
Textbook medicine. You follow the guidelines. You treated the patient. Everything is by the book.
But here's the twist. 1 year later, that same patient walks back into your exam room, and you don't even need to open his file to know something has gone wrong.
Oh, no.
You can see it from the doorway. He's yellow. Visibly, strikingly yellow. The whites of his eyes, his skin. He looks like someone in end-stage liver failure.
Which, for a doctor, is an immediate red alert. You are thinking hepatitis, you are thinking liver necrosis, or maybe, and this is the scary part, drug toxicity.
Yeah.
You are thinking, did I poison this guy?
Your heart just drops. You panic. You rush the blood work. You're expecting to see his liver enzymes, the AST, the ALT, through the roof, indicating massive cell death.
Sure, that's what you'd expect.
But the results come back, and they're totally normal.
So the liver's functioning perfectly.
Perfectly. The machinery is fine. He isn't sick. He hasn't overdosed. He's taking the pills exactly as you told him to. But he looks like a highlighter.
This is such a classic opener for this topic. I'm glad you started here. Because the problem isn't the drug. Not really. And the problem isn't the disease.
The problem is a typo.
A tiny invisible typo in his DNA.
This is the story that opens the chapter in Ketsung, and I think it's the perfect hook for what we're doing today. Because that patient, he had a specific genetic variant called UGT1A1, and that microscopic difference in his code turned a standard, safe dose of medicine into a visible toxic event.
And that highlights the central tension of pharmacology, maybe all of medicine. We design drugs for the reference man, the 70-kilogram, statistically average human.
Right, the person who doesn't actually exist.
Exactly. But biology is aggressively individual.
That is our mission today. We are diving into Pharma 07, Pharmacogenetics. We are going to answer the question, why does one dose never fit all?
We're exploring the genetic basis for variation in drug response, and frankly, we have a monster stack of research today. We have Ketsung, which gives us the clinical scaffolding, the what do I do with the patient?
And then we have Goodman and Gilman, which goes deep, deep into the molecular reasoning, the what is happening inside the nucleus.
The why.
I want to set the expectation right now. This is a conceptual map. We are synthesizing a massive amount of data. If you're listening to this on the treadmill or in the car, don't worry about memorizing every single allele number right now.
No, please don't. That's what the books are for.
But if you are prepping for boards or you're actually treating patients, you need to go back and read Ketsung's chapter on pharmacogenomics. Consider us the guides who help you see the forest so you don't get lost in the trees.
The goal is that the next time you look at a table of star alleles, it doesn't look like algebra. It looks like a patient's story.
So looking at the roadmap for today, what are the pillars here? What are the aha moments we need to hit?
I see 5 big ones. First, we have to reframe how we think about genetics. It isn't just a switch, an on-off thing. It is a probability shifter.
It loads the dice.
Exactly. Second, we're going to master the metabolic phenotypes. You will hear these terms constantly. Poor metabolizers, intermediate, extensive, and ultra-rapid. We need to know what those look like in a human being, not just on a chart.
I'm particularly interested in the ultra-rapid metabolizer. It sounds like a superpower, but as we'll see, it is actually a liability, a huge one.
Third, we have to separate the genetics of handling the drug, that's pharmacokinetics, from the genetics of the drug's target pharmacodynamics. That distinction trips people up all the time.
Okay, handling versus target. Got it.
Fourth is visible genetics, like our yellow man. When does heredity show up as immediate, obvious toxicity?
And the fifth.
And finally, we have to talk about precision with humility. Why, despite all this incredible science, isn't genetic testing a crystal ball yet? Why don't we just sequence everyone at birth?
I love that framing. Precision with humility. All right, let's get into the weeds. Section 1. The biological landscape.
Let's do it. Variation is the rule.
I think there's this misconception, even among smart people, that if you put a drug into a body, the drug does the work. It's like a software patch. You install it and it runs.
I wish it were that simple. But it isn't software. It is a chemical negotiation. Goodman and Gilman makes this point beautifully in the introduction. An individual's response to a drug is a complex interplay.
Okay, so what's in that interplay?
You have the environment. What did you eat for breakfast? Do you smoke? How old are you? Are you taking St. John's wort?
The nurture side of the equation, all the external stuff.
Right. But then you have the nature side. And the data here is just startling. They cite twin studies comparing identical twins who share 100% of their DNA to fraternal twins who share, 50%.
And what do they find when they do that comparison?
For some metabolized drugs, up to 75% of the variability in how long the drug stays in the body, the elimination half-life is heritable.
Wait, hold on. 75%.
3/4.
So if I take a pill and it lingers in my system for 6 hours and you take the same pill and it's gone in 2 hours, 3/4 of that difference is just because of who our parents were?
Precisely. It is hard-coded. It is baked into the cake. And that variation comes down to the code itself, the DNA sequence.
So let's talk about the typos, the variants. I see these acronyms thrown around: SMPs, indels, CNVs. It feels like alphabet soup. Can we break them down? What is the most common typo we deal with?
The most common by far is the SNP. SNP, single nucleotide polymorphism.
Which is just a single letter swap. Is that all it is?
That's all it is. Think of your DNA as this massive instruction manual written in 4 letters, A, C, T, and G. A, SNP is when the manual is supposed to say A, but in your copy it says G.
Just one character out of 3 billion.
Just one. But context matters. Sometimes that change is what we call synonymous or silent.
Meaning the instructions still make sense? The cell can still read it?
Meaning the cell doesn't care. Biology has a failsafe for this. It's called the wobble position.
The wobble position. I remember this from biochem, but refresh me.
So DNA codes for amino acids using 3-letter words called codons. Let's say the code for the amino acid proline is CCA. If you have a SNP that changes it to CCG, the cell still makes proline.
It's like spelling color with a U or without. Color versus color. It reads the same. The meaning is identical.
Exactly. The 3rd letter wobbles. It has some flexibility. So the protein comes out looking exactly the same. No harm, no foul.
But I assume they aren't all silent. That would be too easy.
No. That is where the trouble starts. Some are non-synonymous. You swap that letter, and suddenly the code doesn't say proline, it says glutamine.
And now you have a different amino acid in the chain. You've changed the recipe.
Which changed the shape of the protein. Maybe
Right.
it's folded wrong. Maybe the active site, the pocket where the drug is supposed to sit, is shaped like a square instead of a circle. Now the enzyme is unstable, or it works at 10% capacity, or it doesn't work at all.
So that is the SNP, a small change with a potentially huge impact. What about the others? You mentioned indels.
Indel stands for insertion or deletion. This is a bit more violent. This isn't swapping a letter. This is jamming a new letter in or ripping one out.
Which I imagine messes up the reading frame entirely. It's like taking a letter out of a sentence and shifting everything over.
It can. If you shift the frame, everything downstream turns to gibberish, or sometimes it's an insertion of a whole repeating pattern. Remember our yellow man?
The UGT1A1 guy?
Yes, his typo was an endo. In the promoter region of his gene, the on switch, he had an extra TA repeat, a TA added to the sequence. That extra bit of code made the on switch sticky. It didn't turn on as well.
So less enzyme gets made.
Less enzyme, less bilirubin clearance. Hello, jaundice.
Okay, so indels can break the switch or the protein itself. And the third one, CNVs.
Copy number variations. This is the heavy artillery. We aren't talking about letters here. We are talking about whole pages of the manual.
Entire genes.
Entire genes being photocopied or ripped out. The poster child for this is CYP2D6.
We are going to talk a lot about CYP2D6, aren't we?
We have to. It's the workhorse. Now, most people have 2 copies of the CYP2D6 gene, one from mom, one from dad. But because of copy number variations, some people have 0. The gene is just deleted, gone.
So they have no ability whatsoever to make that enzyme.
None. But on the flip side, and this is a wild part, some people have multiple duplications. They might have 3, 4, 5. I think the record is 13 copies of the gene.
13 copies? How does that even happen?
It's a mistake in DNA replication. But imagine a factory floor. You're supposed to have 2 workers on the assembly line. That's normal. This person has 13 workers crammed onto the same line, all working at maximum speed.
You can imagine the output difference would be immense.
It is massive. And that brings us to the nomenclature. Because when you open Katsung, you don't see the guy with 13 copies. You see these star numbers. CYP2D6, star 1, star 2, star 4. It looks like software versions.
Or patch notes for your genome.
It kind of is. It's the star allele system.
Hmm?
It's a shorthand because saying single nucleotide polymorphism at position 1846 G to A is exhausting and, frankly, impossible to remember.
So walk me through the stars. What is star 1? 1.
Star 1 is your baseline. It's the wild type, fully functional, normal reference gene. If you are 11, you are boring. And in pharmacogenetics, boring is good.
Boring is safe.
Exactly. Now, other numbers define the specific broken parts. For CYP2D6, star 44 is a classic loss of function. It's a splicing defect. The gene is there, but the instructions to put it together are messed up, so it can't be read. It's a brick.
So star 4 is completely broken.
Completely non-functional. Then you have something like star 10, which is common in Asian populations. It isn't broken, but it's unstable. It works, but it's sluggish. It's like a worker who is hungover.
Got it. So you have fully working, slow, and broken. And since we have 2 parents, we have 2 stars.
That is your diplotype.
Right.
You're a combination. You could be 11, normal. You could be a 14, 1 working, 1 broken.
Yeah.
Or 44, 2 broken.
And that diplotype is what determines the clinical reality, which brings us to section 2. We've got the code. Now we need to see how that code runs the factory, the pharmacokinetics.
The metabolic bucket brigade.
I love that image. But Keatsong gets a little mathematical here with the activity score. I want to make sure we don't gloss over this because this is how you actually diagnose the phenotype in practice.
Right. The activity score is a way to turn those star numbers into a simple math problem. You just assign a value to each allele you have.
Okay, give me the values.
A fully functional allele, like star 1, gets a score of 1.0.
1 point.
A non-functional allele, like our star 4, the broken one, gets a 0.
0 points.
And a reduced function allele, like star 10, the hungover one, gets 0.5.
Half a point.
And you just add your 2 copies together. So let's test you. If your diplotype is 11.
1 plus 1 is 2. My score is 2.
Perfect. What if you're a 14, 1 normal, 1 broken?
1 plus 0, my score is 1.
And if you're a 44?
0 plus 0, my score is 0. Total shutdown.
Now we take those scores and dump them into the 4 phenotype buckets. These are the labels you'll actually write in a patient's chart.
Okay, bucket 1. The zeros.
Poor metabolizers, PM. An activity score of 0. Their factory line is stopped. The lights are off. They can't process the drug.
Bucket 2. The intermediates.
Intermediate metabolizers, IM. Activity score of 0.5. The line is moving, but it's struggling. 1 worker is out sick.
Bucket 3. The normals. But they don't call them normal, do they? That would be too simple.
No, pharmacologists love confusing terms. They call them extensive metabolizers, EM. An activity score of 1.0 to 2.0, this is the majority of the population. The system works as designed.
And finally, the people with 13 copies.
The ultra-rapid metabolizers.
Yeah.
An activity score greater than 2.0. Their factory is running at breakneck speed, churning out product.
Okay, so we have poor, intermediate, extensive, and ultra-rapid. This feels like an abstract categorization until you swallow a pill.
Correct. It's just theory until it meets physiology.
Let's make this real. Let's talk about codeine. Because I think this is the example that scares people the most when they finally understand it.
It should. Codeine is a ubiquitous drug. It's in cough syrup. It's Tylenol #3. It has been used for decades.
And the assumption is, I have pain, I take codeine, the codeine soothes the pain. Simple.
That is the assumption. But chemically, it is completely wrong. Codeine is a prodrug.
Explain prodrug for us.
It means the molecule you swallow is biologically inactive. Codeine itself has very, very low affinity for the mu-opioid receptors in your brain. It doesn't really do anything on its own.
It's a dud.
It's a dud until it hits the liver. Specifically, until it hits the CYP2D6 enzyme. That enzyme metabolizes the codeine, it strips off a methyl group, and converts it into its active form.
Which is?
Morphine.
Wait, really? When I take Tylenol #3, my liver is manufacturing morphine inside my body.
Exactly. You are a walking morphine factory. That is the only reason the drug works at all. But now, let's overlay our phenotypes.
Okay, let's take the poor metabolizer. The guy with the 44 genotype. His activity score is 0.
He swallows the codeine, it goes to the liver, it looks for CYP2D6. But the factory's closed. The lights are off. There are no workers.
So no conversion happens.
0. The codeine just floats around in his blood doing nothing until his kidneys eventually filter it out and he pees it out. He gets absolutely no pain relief.
And this creates a really dangerous dynamic in the clinic, doesn't it? A real ethical problem.
It does. Picture it. The patient comes back in agony. Doc, the pills aren't working. I'm still in so much pain. I need something stronger.
And the doctor, who believes codeine works, looks at the patient and thinks,
Drug seeker. Addict. They think the patient is lying to get more pills, to get a bigger high. but the patient is telling the biological truth. Their DNA literally cannot unlock the medicine.
That is tragic. But the flip side seems even more immediately dangerous. The ultra-rapid metabolizer.
The person with 3, 4, 10, 13 copies of the gene.
They take the same standard dose of codeine?
The dose that's safe for 90% of people. But their liver, with its 13 factory workers, grabs every single molecule of codeine and converts it to morphine instantly.
So instead of a slow, steady trickle of pain relief over a few hours?
They get a massive instantaneous spike. A morphine overdose from a standard dose of codeine.
And that looks like. What are the signs?
Extreme sedation, pinpoint pupils, and most dangerously, respiratory depression. They just stop breathing.
And there are cases of this ending badly, especially in children.
Tragically, there were high-profile cases of kids getting tonsillectomies, a really common procedure. They were given standard codeine for recovery. Some of them were ultra-rapid metabolizers. They went to sleep and never woke up.
Just because of a copy number variation.
Yes. Because of that, the guidelines changed. The CPIC guidelines, which we will talk about later, now effectively say, do not give codeine to poor metabolizers because it won't work, and absolutely do not give it to ultra-rapid metabolizers because it might kill them.
So if you don't know which one you are, you're gambling.
You are rolling the dice with loaded probability. And considering CYP2D6 metabolizes about 25% of all drugs on the market, antidepressants, beta blockers, antipsychotics, this isn't some niche problem. This is a massive public health blind spot.
It's incredible that we still prescribe these drugs without checking. But let's look at another one. Clopidogrel. Brand name Plavix.
Plavix is a huge drug, a blockbuster. It's an antiplatelet agent, a blood thinner.
Usually given after someone has a stent put in their heart, right, to keep the plumbing open.
Correct. You put a metal stent in a coronary artery. You do not want a blood clot forming on that metal. If it clots, the patient has a heart attack. So you give clopidogrel to keep the platelets slippery and from sticking together.
And let me guess, clopidogrel is also a prodrug.
It is. It relies on a different enzyme, CYP2C19, to activate it.
Okay, so same logic applies. If I am a poor metabolizer of CYP2C19...
You take the pill every morning, like a good patient, it goes to your liver. But the factory that's supposed to turn it on is, again, closed for business. The drug doesn't activate, your platelets remain sticky.
But I think I'm protected. My doctor told me I'm protected. I'm taking my pill every morning.
And then 3 weeks later, you have massive chest pain, stent thrombosis. The stent clots off. It's a catastrophic therapeutic failure, and it happens while the drug is technically in your system.
Now, this is where the Katzung text brings in the ancestry component in a big way, because the distribution of these broken alleles isn't random across the globe.
No, it is not. And this is why knowing your patient population matters so much. The loss of function variants for CYP2C19, the broken alleles, are present in maybe 2 to 3% of European populations. It's relatively rare.
But in East Asian populations?
In Chinese and Japanese populations, the frequency is closer to 15 to 20%.
Wow, 1 in 5.
Potentially 1 in 5 patients walking into a clinic in Tokyo or Beijing might be a talk. Poor metabolizer for this life-saving drug.
That changes the calculus completely. If I'm a doctor treating a patient of East Asian descent, prescribing clopidogrel blindly feels like a much, much riskier bet than for a European patient.
It is. And the FDA actually put a black box warning on clopidogrel about this specific issue. It's one of their strongest warnings. They recommend checking the genotype or just using a different drug like ticagrel or prasugrel that doesn't depend on CYP2C19 activation.
So that is pharmacogenetics. That is the factory, the drug getting into the blood and becoming active. But that is only half the battle. Because once the drug is active, it has to hit a target.
Right, it has to do something. That's pharmacodynamics.
And this is where the story gets even more complex, because what if the target moves?
Or what if the target is, smaller than usual? This brings us to the most notorious drug in the pharmacopoeia, I think.
Warfarin.
Warfarin, also known as Coumadin, and rat poison.
Literally. It was developed as a rodenticide before it was a medicine. It's a blood thinner, but it has a very narrow therapeutic index.
Meaning the difference between the dose that prevents a stroke and the dose that causes a brain bleed is tiny.
Razor thin. And warfarin is a perfect storm for genetics because it's a double whammy. It gets hit by a genetic variation in both kinetics and dynamics. Okay, let's peel this onion. Let's start with variable 1, kinetics. How the body handles it.
Warfarin is cleared from the body primarily by the enzyme CYP2C9.
Another CYP liver enzyme.
Yes. Now, there are common variants, specifically the STAR2 and STAR3 alleles. that make this enzyme slow. They're particularly common in European populations.
So if I have those alleles, I'm a slow clear.
You are. You take the warfarin, your body doesn't get rid of it efficiently, the levels in your blood climb higher and higher each day, you are at a massive risk of bleeding on a standard dose.
Okay, that's the drain being clogged. Now for variable 2, the dynamics.
The target. Warfarin works by inhibiting an enzyme called VKORC1.
Vitamin K, epoxide reductase complex 1.
You've been studying. Yes. This enzyme's job is to recycle vitamin K, which your liver needs to make clotting factors. Warfarin shuts down the recycling plant.
So warfarin is the arrow,
Yeah.
and VKORC1 is the bullseye.
Exactly. Now imagine a patient who has a genetic mutation in the promoter region of the VKORC1 gene. It's not in the gene itself, but the on switch. This mutation is very common in Asian populations.
And what does that promoter mutation do?
It makes the body produce less VKORC1 enzyme naturally. From birth, they just have less of it.
So they have fewer bullseyes to begin with.
Right. If you have fewer targets, you don't need many arrows to hit them all.
You become hypersensitive to the drug.
Extremely hypersensitive. You need a tiny, tiny dose to get the same anticoagulant effect.
So now imagine the nightmare patient, the perfect storm, the one you have to watch out for.
A patient who has the CYP2C9 slow clearance gene.
So the drug builds up in their system.
And they have the VKORC1 low target gene.
So they're super sensitive to even a small amount of it.
If you give that patient a standard starting dose of warfarin, say 5 milligrams, you will anticoagulate them into a crisis within days. They will bleed out.
It really shows that trial and error dosing isn't just inefficient, it's truly dangerous.
It is. And that's why the CPIC guidelines for warfarin are actually an algorithm. You don't just guess. You plug in age, weight, CYP2C9 status, and VKORC1 status, and the computer spits out the recommended starting dose. It is precision medicine in action.
I want to shift gears a little bit. We've talked about drugs not working, like with codeine. We've talked about drugs working too well, like with warfarin. But sometimes genetics creates a totally different kind of horror show, straight up toxicity.
Visible genetics, when it shows up on the outside.
Let's circle back to our yellow man. We left him in the waiting room at the beginning of the deep dive.
Right, so his gene was UGT1A1.
And you said that enzyme is a kind of trash collector?
Essentially, its main job is to take bilirubin, which is the yellow breakdown product of old red blood cells, and conjugate it. It tags it with a sugar molecule, which makes it water-soluble so it can be excreted in the bile and pooped out.
Crude, but effective.
Now, there is a common variant called UGT1A1*28. It's that insertion we mentioned earlier. If you have it, your trash collector is lazy. You operate at about 30% of normal capacity.
And this condition has a name, right? It's not just a lab finding.
Yes, it's called Gilbert syndrome. About 10% of the population has it. Usually it's completely benign. Maybe you get a little yellow if you get the flu or you're fasting for a long time. No big deal.
But our patient took atazanavir.
And atazanavir is a known inhibitor of the UGT1A1 enzyme.
So he had a lazy enzyme to begin with, and then the drug tied the hands of the few workers he had left.
Exactly. A complete bottleneck. Bilirubin backs up, spikes in the blood. He turned yellow. Now, for him, it was mostly cosmetic. He looked terrible, but he wasn't dying. But if you take that same gene and pair it with a different drug, it becomes deadly serious.
Irinotecan.
A chemotherapy drug used for colon cancer.
And chemo's already toxic. That's the whole point.
Right, but you need to be able to clear it from your system. Irinotecan breaks down into a metabolite called SN38. SN38 is the killer. It destroys the cancer cells. But it has to be deactivated and cleared by, you guessed it,
UGT1A1.
If you have that 28 variant, the lazy trash collector, you cannot clear the SN38. It builds up to massive toxic levels in your body.
And what does that do to a patient who is already sick with cancer?
It completely wipes out their bone marrow, leading to severe neutropenia.
Yeah.
They have no immune system left.
Uh-huh.
And it causes severe life-threatening diarrhea. We sometimes call it cholinergic syndrome. It isn't just an upset stomach. It's severe dehydration and electrolyte collapse.
So patients end up in the ICU or worse.
Or the morgue. And it's entirely predictable based on that one little insertion in the promoter gene.
There is one more example in this section that really stuck with me because it's not about liver enzymes at all. It's about the immune system going rogue. HLA-B.
The human leukocyte antigen system. These are the genes that control the flags on the outside of your cells. They're constantly presenting little pieces of what's inside the cell to your immune system. They basically tell your T cells, this is self, don't shoot, or this is invader, kill it.
And sometimes they get confused by a drug.
Yes. The classic example is the drug abacavir, used for HIV.
A different HIV drug from our first story.
Right. There is a specific allele called HLA-B star 57.01. It sounds like a coordinate from a star map.
It does.
If a patient carries this specific allele, the abacavir molecule has a shape that allows it to bind perfectly into the peptide groove of that specific HLA receptor. It changes the shape of the cell flag.
So suddenly the immune system looks at the body's own cells.
And sees a foreign invader. It doesn't recognize them anymore. So it launches a massive, total war against the body's own tissues.
A hypersensitivity reaction.
And not a mild one. We're talking Stevens-Johnson syndrome or toxic epidermal necrolysis. The skin blisters and peels off. The mucous membranes, eyes, mouth, internal organs are attacked. It is absolutely horrific.
And this is binary, right? It isn't like the slow metabolizer scale we were talking about before.
It is essentially binary. If you have the gene, the risk of this reaction is massive, over 50%. If you don't have the gene, the risk is almost zero.
And because the stakes are so high, I mean, skin peeling off, this changed the rules of medicine.
It did. Godsung notes that this is one of the few examples where genetic testing is mandatory. You cannot prescribe abacavir in the U.S. or Europe without a negative HLA-B57.01 test on file, period.
That is a true success story for the field. We identified the gene, we developed the test, we implemented it, and we stopped the reaction from ever happening.
Absolutely. It went from being an unpredictable side effect to a preventable medical error. That's a huge shift.
One more in this toxicity bucket. G6PD deficiency. This one feels historic, almost evolutionary.
It is. It's an X-linked trait, so it affects men much more often than women. And it is actually linked to evolutionary survival. Having this deficiency provides partial protection against malaria.
Oh, that's fascinating.
That's why it's so common in populations from malaria-endemic regions like Africa, the Mediterranean, and parts of Asia.
But in the modern world, with modern drugs, it causes problems.
Yes. G6PD is an enzyme that protects red blood cells from oxidative stress. Think of it as the shield that keeps the red blood cell from rusting. If you are deficient, your red blood cells are fragile. They're vulnerable.
So if you take a drug that causes oxidative stress,
like Primaquine, which is an anti-malarial, ironically, or resburicase, a chemo drug. The drug creates stress, the cell has no shield, and it bursts.
hemolysis.
Widespread hemolysis. The patient becomes anemic very, very quickly.
It's amazing how these ancient survival mechanisms like malaria protection can turn into modern medical liabilities.
That is the trade-off of evolution, isn't it?
Right.
What helps you survive in one environment can be a risk in another.
So we've covered the biology, the kinetics, the dynamics, the toxicity. We know this stuff is real. We know it works. But this brings us to the final and maybe most frustrating question, Section 5. So what?
Precision with humility.
If we know all this, why don't I have my genome card in my wallet? Why don't we sequence everyone at birth and just have this information ready?
It is the billion-dollar question. And the answer is a mix of biology, economics, and practicality.
Let's start with the biology. You made a distinction earlier about ancestry versus race. Why is that so important here?
Because drugs don't care what box you check on a census form. Race is a social construct. Ancestry is your genetic history, your geographic origins.
Give me an example of where they diverge.
Take an African-American patient. Socially, they might identify as black. But genetically, their ancestry might be a complex mix of West African, European, even Native American heritage.
And because African populations have the highest genetic diversity on Earth?
The prediction is harder. A variant that is a slam-dunk predictor in Europeans might not even exist in an African population, or it might not have the same effect because of other modifying genes in the background. Goodman and Gilman describes cosmopolitan polymorphisms, those are the ancient ones found in everyone, versus population-specific ones that arose after humans migrated out of Africa.
So the one-size-fits-all test doesn't exist either. A test designed in Europe might not work well in Asia.
Exactly. And then you have the complexity problem. Most drug responses are not monogenic.
Meaning driven by one single gene, like CYP2D6 and codeine?
Right. Most things like how much your blood pressure drops with a beta blocker or your response to an antidepressant are multigenic. It's 100 tiny dials turning at once, each contributing a small amount. Plus the environment. We just don't have the math to solve that equation yet. Goodman and Gilman has a great figure, 7.3, that visualizes this. The more genes involved, the smoother the bell curve, and the harder it is to pick out the one cause.
And then there's my favorite term from this deep dive, phenocopying.
This is the ultimate curveball. Phenocopying means looking like the genotype without having the genotype.
How does that happen? Can you give an example?
Of course. Remember the poor metabolizer of CYP2D6? The factory is closed because of their genes?
Yep, the 44 person.
Well, you can be a genetic, extensive metabolizer perfect genes 11. But let's say you are taking fluoxetine Prozac for depression.
Okay.
Fluoxetine is a potent inhibitor of the CYP2D6 enzyme. It physically blocks the enzyme. So while you are taking Prozac, your factory is functionally closed.
So biologically, I am acting just like a poor metabolizer, even though my genes are fine.
You are a phenocopy. A genetic test would come back and say you're safe to take codeine. But if you take it while you're on Prozac, it won't work. The genetic test cannot see the other pill bottles on your nightstand.
That is a huge limitation. It isn't just about the code, it is about the entire context of the patient.
It's always about context. Always.
And finally, there's the money. The simple question of cost versus utility.
All right, Ketzung has a graph of this. It plots tests ordered versus clinical utility. Just because a test exists doesn't mean it's useful. Does knowing the genotype actually change the outcome for the patient and save the healthcare system money in the long run?
It's a high bar to clear.
A very high bar. For abacavir, yes, absolutely. It's a no-brainer. It prevents a life-threatening reaction. For warfarin, the data is actually mixed. Sometimes simpler clinical algorithms based on age and weight work just as well. We have to prove the value before we spend the money.
So where does that leave us? What is the state of the art right now for a clinician?
The gold standard is the CPIC guidelines. That's the Clinical Pharmacogenetics Implementation Consortium.
What do they do?
They don't tell you whether to test. That's a cost-benefit decision for the health system. They tell you what to do if you already have the data. If genotype is X, then the recommendation is Y. They translate the lab result into a clinical action.
And the dream the future is preemptive genotyping.
That is the holy grail. The idea that your genetic data sits in your electronic medical record. Quiet. Invisible. Then, 5 years from now, your doctor types in a prescription for clopidogrel.
And a pop-up appears on the screen.
A clinical decision support alert. A big red flag that says, stop a P. Patient is a CYP2C19 poor metabolizer. High risk of treatment failure. Consider alternative agent like prasugrel.
No waiting for a test, no swabbing the cheek. The data is just there protecting you in the background.
That's where we are heading. Slowly. Integrating the code into the care.
It has been a fascinating journey. We started with a yellow man and we ended with a computer algorithm.
It really is a paradigm shift in medicine. We're moving from the average patient model to the individual patient model.
And understanding that genetics isn't magic, it just shifts the probabilities. It explains why the standard dose fails some, harms others, and works perfectly for the lucky ones.
It brings a scientific explanation to what clinicians have seen for centuries at the bedside, that every single body is different.
Before we sign off, I want to leave the listener with a provocative thought. We've talked about reading the code. What about writing it?
Well, Goodman and Gilman hints at this in the conclusion of their chapter. We are entering the age of CRISPR and gene editing.
Go on.
Right now, if you have a bad liver enzyme variant that causes toxicity, we just change the drug or lower the dose. We work around the defect.
But could we fix the defect itself?
That is the question. Could we eventually deliver a therapy that edits the UGT1A1 gene in the liver to cure Gilbert syndrome? Or something even closer to reality, could we use iPSC's induced pluripotent stem cells to take a skin cell from you, turn it into a liver cell, and grow a mini version of your specific liver in a petri dish?
An avatar liver.
Exactly. We test the drug on your avatar. If it turns yellow in the dish, we don't give the drug to you. We make our mistakes in the lab, not in the patient.
That is the sci-fi future that is slowly but surely becoming reality. Incredible.
It's an exciting and humbling time to be in medicine.
Well, that wraps up our doom dive into pharmacogenetics. Remember, we just scratched the surface here.
The podcast is the map. The book is the territory. Please open Ketzung for the allele tables and the clinical guidelines. Open Goodman and Gilman for the molecular diagrams of indels and SNPs.
Thanks for listening. Stay curious and remember, one dose never fits all.
See you next time.